Today we're going to start talking about logarithms, and logarithms have a bad reputation with students because the first time you learn them, they are a little bit difficult to get your brain wrapped around. And I don't think that's because the concept is so difficult, but rather that we have this awful notation for them that makes it a little bit harder to understand what's going on. So I'm going to try to ease the burden on this by showing you this triangle of power. And I learned about the triangle of power from a guy named Grant Sanderson. He's a math YouTuber, and I'm going to post a link to his video in the description for this one. So if you want to learn a little bit more in depth about this triangle of power, he goes way further with it than I'm going to go. But I do think it helps clear things up with logarithms a little bit. Okay, so let's start off with an exponential rule that we're all pretty comfortable with. And that is 2 times 2 times 2 is equal to 8. 2 cubed is equal to 8. So the way you write that on the triangle of power kind of looks like regular exponent. 2 cubed is equal to 8. All right, so we know that this means that 8 is equal to 2 cubed. This triangle relationship also tells us that the cube root of 8 is equal to 2. All right, and then the 3 also gets its own notation involving the other two numbers. 3 is equal to the log base 2 of 8. Okay, so these are 3 different notations that are basically saying the same thing about these numbers, 2, 3, and 8. So when we are talking about logarithms, we're talking about the exponent in that relationship of 3 numbers. Okay, so let's draw another triangle. All right, so if I draw this triangle, we know that means 3 to the 4th. So the bottom number on the right in the triangle needs to be 3 to the 4th power, which is 81. So 81 is 3 to the 4th. 3 is the 4th root of 81. And then with our new notation with logarithms, we're going to say this is the log base 3 of 81. So again, the 4 is the exponent in the relationship, and it's also equal to the logarithm. And the base on the logarithm, that little subscript that's hanging down, comes from the bottom left of the triangle. And then the argument of the logarithm, the number that's bigger in parentheses, is the bottom right of the triangle. Okay, so let's do one more triangle. All right, so this one, I've given you the bottom left number is 8, the bottom right number is 64. So now we're looking for the exponent. So 8 to the what is equal to 64? Well, I have to square it. So the number that goes up top here is going to be a 2. And what we just did, which felt a little bit easier than it normally does in a pre-calculus class, is we evaluated a logarithm. We found that the log base 8 of 64 is equal to 2. All right, so if you can fill out the top of this triangle for any pair of numbers that I give you on the bottom, you can evaluate logarithms. All right, so this awful thing is how we usually introduce logarithms to students. The logarithm with base b is the inverse of the exponential function with base b. And this does feel a little bit inversey in that the input of the logarithm is the output in the exponential equation, and the output in the logarithm is what's the inside of the exponential equation. So they are swapping inputs and outputs, which is what inverse functions do. So it does feel a little bit that way, but this is a jumble of letters and it's really difficult to keep it straight in your head. So I'm gonna do 2 things. I'm gonna write this down with the triangle, but first I'm gonna rewrite this just with different letters. So I'm gonna rewrite this as the log base d of a equals n. And then I'm going to line up those 3 letters with the b, y, and x over on the right. Okay, so the b was in place of the base of the logarithm. That was a big D. And then y was the number on the right. That's going to be n. And then the x was the argument of the logarithm. That is the capital A. So all I did there was pattern recognition and kind of lined up the letters in the same places in the log and the exponential equation. And so now the exponential equation reads DNA, and the log equation is logardan. And so this will help you to keep all of those letters in the right place with the notation. And again, let's go back to our triangle of power. If I rewrite the exponent notation, which feels familiar, d to the nth power equals a, that's our DNA. And then from the last slide, you can remember how we were writing that logarithm notation, that n is equal to the log base d, because it's on the left, and a because it's on the right. And you get that logardan, dA is equal to n. All right, so whichever notation, the logardan or using the triangle of power feels more comfortable to you, go ahead and do that. Okay, so this example and the next one is just going to get us used to converting exponential and logarithmic equations back and forth between each other. Remember that they're just two different ways of saying the same thing about a relationship of these three numbers. Okay, so this equation is 2 to the 4th equals 16. I'm going to put that on a triangle. So I draw my triangle and I say 2 to the 4th equals 16. And then we know that the logarithm is the exponent. So I'm going to go up top and I'm going to write the log. The base comes from the bottom left of the triangle. And what's inside the logarithm comes from the bottom right. So that's the 16. All right, so the log form of this equation is log base 2 of 16 equals 4. Okay, and again, if you would rather just line that up with the logardan and dna, you could think of this equation as d to the n equals a, and then rearrange the letters so you get logardan. So log base d of a equals n. Okay, so triangle or dna logardan, whichever is more comfortable for you. Either way, your answer is this logarithmic equation. All right, let's convert this one. This is a log equation, log base 4 of 64 equals 3. If I do this one with the triangle, this one will be kind of harder. Okay, so I know that the 4 and the 64, the base and the argument of the logarithm, are the two numbers that go on the bottom. Okay, so I'm going to put the 4 over here and the 64, and then we know that the logarithm is the exponent that goes up top. All right, and that gives me the equation 4 cubed is equal to 64. And then, like I said, you could also just stick with the logardan notation. So I could think of this as logardan. And then just arrange the d, the n, and the a into d, n equals a notation. All right, so let's try our hand at being logarithm calculators. So we're asked to evaluate the log base 6 of 36. So again, when you're evaluating logarithms, you're looking for that top part of the triangle. You're looking for the exponent. So I'm going to draw my triangle of power. And I know that the 6, the base, goes on the bottom left. The argument of the logarithm goes on the right. So we're looking for the log, which is the exponent. What is the exponent that you have to put on a 6 to get 36? We have to square it. So this logarithm is equal to 2. Next up, log base 4 of 1/4. Let's draw our triangle. So there's 4 and 1/4. Base always on the left, argument always on the right. The logarithm is always the exponent. So what exponent do I need to put up here at the top to give me 1/4? This one might be helpful to actually go ahead and write in exponential form. So we're trying to figure out 4 to the what is equal to 1/4. Okay, well, the only exponent I know that will turn a whole number into a fraction is a negative exponent. So I need a negative something in the exponent, and it needs to match the exponent of the 4 in the denominator, which is just kind of hanging out being 4 to the first. So this should be a -1, and that's the exponent that belongs at the top. So that's the value of the logarithm. So -1's our answer. All right, how about log base 7 of 1? Let's draw our triangle. So the base goes on the left, the argument goes on the right, and we're looking for what exponent we need. Okay, so again, if it helps you kind of put a blank there, we would say 7 to the what equals 1. And it actually doesn't matter that that's a 7. The exponent you need on anything to give you 1 would be 0. 7 to the 0 equals 1. So that's the value of this logarithm. All right, log base e of the cube root of e. Okay, let's write this on our triangle. We're gonna have to remember a couple of things that we've learned recently. E on the bottom left, cube root of e on the bottom right. And we're looking for an exponent that's gonna turn e into the cube root of e. Let's remember that e is that number 2.71828 and so on. And let's also remember our exponent rule. A to the m over n is equal to the nth root of a to the m. All right, so we've got down here e to the, well, the cube root of e really to the first. Okay, so the exponent that will give you the cube root of e is e to the 1/3. Okay, the denominator of that exponent always tells you what kind of root you have. All right, so I need e to the 1/3 to get the cube root of e. So that's what belongs up top on my triangle of power, and that's what our logarithm is equal to. All right, what else do we got? Log base 10 of 10. Okay, so again, I'm going to draw my triangle, the base on the bottom left, the argument on the bottom right. 10 to the what is equal to 10. The exponent we need is a 1. 10 to the first power is equal to 10. So that's the value of our logarithm. Now that one wouldn't have mattered if they're both 10s at the bottom, both 5s at the bottom, or both 628s at the bottom, right? Anything to the 1 is equal to itself. Last one, log base 3 of -9. This one's tricky. So let's draw our triangle. So let's see, 3 to the what is equal to -9. Okay, so the first thing that pops into your head is probably 2. That's not going to work because that would give me +9, doesn't make it negative. So you might be thinking maybe -2. But that just creates a fraction, right? That doesn't make anything negative. That would give me 1/9. Okay, that's not what I'm looking for. And even if you try like a fraction 3 to the 1/2, that tells me a square root, right? That's equal to the square root of 3. This is actually impossible to do. It was a trick question, kind of. You can't get a negative number by exponentiating a positive number with some sort of exponent. So up here, we're going to say that this is undefined or does not exist. It just can't happen. All right. And it's going to turn out to be the case that we're not going to be able to take any logarithms of any negative numbers. Logarithms are a bit like square roots in that case. They reject them as far as the real numbers are concerned. All right, so that's it for evaluating logarithms. I'll see you in class to learn more about their graphs.